ask a close?
Yes, absolutely. Yes.
I'm not exactly sure how to ask this, but I've just been having trouble with this box on wedge on ramp problem.
Okay.
On like how to set up the like the coordinate axes and like what the easiest way to do it is.
Sorry, may I just take this?
Yeah.
Thank you.
Let's see, it's not necessarily an angle there. So mask 1, mask 2, mask R. I have some external force F there. I have ground. Beta. Alpha.
Good. And we get, assume that MR accelerates to the right, so that's the direction of acceleration. M1 and 2 are traveling at constant velocities, all right, so acceleration is 0. For these two. All right, so, and it was, what is the equation system? The equations of motion for just MR.
For MR, yep.
Okay. So as you go down the process, we have the facades process. And considering the different medium, this is resolution is not quite as good for that approach, right? Bigger. So force diagram's already been done. Acceleration was given within the context of the problem. So, and we're taking it to there. So, coordinate system. What would be a natural direction for the coordinate system for the wedge?
That would seem to just be like up and right.
Okay. So one of them in the direction of acceleration. I'll cleverly call it I hat, and then that direction J hat. All right. Do we need to decompose any vectors? Or any vectors not horizontal or vertical?
Y2.
Okay.
F2.
And that's it. Because F is given to you, presented horizontally. I don't know if I state that explicitly, but the way it's drawn.
Mm-hmm.
FR is parallel to the ground, WR is perpendicular to the ground, YR perpendicular to the ground. So we just have to break these two vectors up.
Okay.
F2 is probably going to be the simpler one because it's coming down at some angle alpha. And we just need to know how much is down and how much is over.
Mm-hmm.
And then Y2 is perpendicular to it. And so for F2, the vertical component will be sine, related to sine. So for Y2, the vertical will be cosine.
Okay.
So ultimately, is that master set or is that just an old test?
This is just an old test.
Okay. So if I have F2 right here, this would be F2 sine alpha, F2 cosine alpha. Y I am breaking up, or Y2, I'm breaking up Y2. why I'm breaking up is not a question. And so vertical and horizontal will flop trig functions because of the perpendicular nature of those two. So that's y2 cosine alpha that way, y2 sine alpha that way. And so ultimately, we've taken these 1, 2, 3, 4, 5. We've taken the 6 forces here, and we now have 8 because we split these two up.
Yeah.
So if I think about, shape doesn't really matter here. So I have F going to the right. I have FR going to the left. I have WR going down. YR going up. And then the two I broke up, we have y2 cosine alpha down, y2 sine alpha to the left, and then for friction we had f2 cosine alpha to the right and f2 sine alpha down, I believe. Yep.
Okay.
And so now the equation of motion.
Okay. And then, so for your equations of motion, you just take all the ones in the same direction, make them equal to the mass times acceleration of the system?
Yeah. And in this particular case, since I said acceleration was to the right, then the horizontal would be equal to m sub r times whatever a.
Okay.
And then vertically, it would be equal to 0 because there's no acceleration vertically.
Okay. So you really only have one useful equation of motion?
I wouldn't say only one useful because friction's involved here.
Okay.
You do need the other equation in order ultimately to solve for YR, so we can find FR if we wanted to keep going.
Okay. I think what was tripping me up when I was trying it on the master set version, it was asking for the M1 equations of motion.
Right.
And my thought process was it would be, in that situation, would you think it'd be easier to decompose the force of gravity instead of the
other two?
Yeah. And
Yeah,
like
probably.
have your coordinate axes like sort of tilted?
That way you're only breaking one up. So in that particular case, because these two are not accelerating, they're in dynamic equilibrium, then it really doesn't matter what coordinate system you pick.
Okay.
So some people just naturally go for that, but not necessarily. That makes a lot of sense because you're only breaking up the weight. And so you would need to figure out what is that angle. That's the tricky part of figuring out that angle.
Oh, okay. Yeah.
Because weight would be, I'm going to label it temporarily as theta. Theta better not show up in the final answer because theta is not defined in the problem.
Mm-hmm.
Some students really like using theta a lot. Possibly something innate or the fact that I use theta a lot. But theta is not in the problem, so theta should not be in the final answer. Also, another common problem I see is that that's an alpha. That's the letter A. Now, some people will then stick something up like that to make it look like an alpha. That's fine, but there is a difference between A and alpha. Mark and pull. So if that's theta, that angle there is theta. That angle there is alpha, because that is parallel to that, and those are alternate interior angles. And so I know that alpha plus theta is equal to beta. Therefore, theta is beta minus alpha. So weight would break up as in a component down this way of W1. See, down the ramp would be sine, so sine of theta or beta minus alpha. And in this direction, W1, cosine of beta minus alpha.
Okay.
if you get the wrong angle, you know, well, it depends on how many equations of motion that you're going to do. But for one equation of motion, if you got the wrong angle, that's minus 1 out of 10 points. If you're doing 4 equations of motion total, that's 1 out of 40 points.
Okay.
Although it'll probably end up being 2 points, because if you mess that angle up, that angle's messed up too.
Yeah.
2 out of 40. I would recommend, no, not necessarily. It's a lot of fun grading this problem, sarcastically, because for these especially, you'll have a group of people who will choose that as your coordinate system, and other people will choose that as the coordinate system. So,
Yeah.
you know, it's multiple solutions.
Yeah.
If you ever saw my notes for grading that, it's, you know, I get used to that, and then someone else comes up with a completely different one because they want it to match, you know, that slope right there.
Yeah, you could make this one really complicated.
Was your question answered?
Yeah, that
Okay.
was good.
Other questions? What I'm wondering is, how long are those lines on the backboard going to be there? I'm not indicating it should be erased. I'm just curious, are those going to be there 5 months from now? All right.
That's us
Think-
leaving our mark.
What was that?
That's us leaving our mark.
That's right. I will say, as far as these problems go, I think there's a general progression in the labs that I started out with relatively simple ones, and then it got really complex, and then I thought, ooh, well, I went too far, and then I started scaling back. I think originally it would have been, what are the equations of motion of all 3 masses?
Oh, okay.
All right, so we dealt with black holes last time, and so now let's do the hard problem. Hot one ran. Box of some mass m, and there's of course a spring involved. So let's first start out with the problem. This is some angle theta. Let's make that around 37 degrees. And I actually had numbers. So mass is 5 kilograms. Let's put this on a strange new world where g is equal to 10 meters per second squared. Should save us a couple seconds worth of work. The distance from the mass to the spring is L, which is 3 meters. And let's just go ahead. The sine of 37 degrees, 0.6, and the cosine of 37 degrees, 0.8. And there's times where I give out the really long 10-digit one, the 36.8, whatever. That's so that these come out nicely. The spring needs a spring constant. And I let K equal 20 newtons per meter. And so the first time we're going to do this without friction. Then we'll throw friction into it. And so the question is, how far will the spring compress? And typically, the first letter should be capitalized. What the heck? Let's just do it.
Is this alpha, or is that length? Like where
That-
it's 3 meters?
That's length.
That's length,
That's supposed to be an L.
okay. Okay.
When I first started solving it, I had a capital L and a lowercase l, and then ultimately one of them went away. So if you want to do a capital L, there's no problem with that. Now, I don't know, so try that again. My unknown is how far the spring will compress. And so I'm going to create a letter called X. X is basically what I'm trying to find. And we're going to do this with energy. So what are the forces that will be acting on the mass?
Gravity or weight?
All right, so we got weight,
Normal force? Friction?
no friction to start with. Eventually we'll add that in.
Okay.
It's going to be one other force acting on.
Tension.
Pardon?
Tension.
Tension is going to require it's being pulled.
Did you say normal force? Did you count?
Mhm.
You said normal force.
I think somebody said normal force.
Yeah.
Is that a
Normal
convention?
force from the spring?
He said no friction.
Okay.
Well, it's not touching the spring yet, so it's like.
You mean?
At some point it will be. All right, so normal force from the ramp definitely is involved in the forces involved. We're not going to call it normal force from the spring, even though I guess officially it is a normal force. It is what we're just going to call a spring force, an elastic force.
Would that be under other? Or would we consider it as normal, but just different?
There we go. F-tongs.
Excellent.
Saint Fong. Whatever. All right, so we're going to have this spring force. It's an elastic force, really. I don't want to use E just because E is reserved for electric later in 152, which reminds me, I want to talk about that before we're done. So the question is, we have the gravitational force, we have the spring force, and then there's a normal force from the ramp.
And friction. No, you said friction.
Not quite yet.
Okay.
Which of these three forces are non-conservative?
Normal force and elastic force.
Just normal force.
Just normal.
How do we know the elastic force is going to be non-conservative?
It was on the list. I mean, there are a couple ways of doing it, but the elastic force is a conservative force.
Okay.
There is a potential energy formula associated with it. I thought I derived that last time. Or is that just my imagination?
I think it did. I just don't remember.
You derived what?
The 1/2 kx squared, or k delta x squared?
Oh, yeah.
Yeah.
I think I remember that.
Yeah, that's the potential energy formula associated with the elastic force. Therefore, elastic force is conservative. All right, so these are conservative. The non-conservative force, the normal force coming from the ramp, how much work will that do? Why?
Because it is not accelerated, because it's non-conservative.
That's,
That not the
Move
reason.
it.
It's,
pardon?
It doesn't move it.
Right. It's not aiding or abetting, wrong word.
Acceleration.
Aiding, it's not adding, it's not making it go down the ramp and it's not making it go up the ramp.
Like the ski problem.
Yes, exactly like the ski problem. Except this time our slope is constant.
Is it also because it's acting on a different, like the acceleration, let's call this, if this is I hat, because the normal force is on the like J hat axis, is that the reason?
Ultimately, yes, because if you do because work is a dot product, force dot displacement, which means it's the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So a little bit more underlying, not just I hat and J hat, the fact that I hat and J hat are perpendicular. The fact that the normal force is perpendicular to the displacement,
That's
the angle is 90 degrees, therefore no work being done.
right.
It's not adding to or detracting from directly the movement.
so wouldn't there be a normal force down the ramp though? Since there's a normal force up. I feel like I had the same exact question last time.
There's not a normal force. Normal force is a pushing force.
Okay.
So what pushing force is there down the ramp?
Okay, I see.
Question about that.
Yes.
Let's say there were a normal force pushing down the ramp, like a person pushing on this box.
Right.
That would be a normal force, and it would be non-conservative, but it would contribute to the work of the problem because it's,
Correct.
okay. Right.
And we will get it after this example, we will throw friction into it, which is similar, that would be similar to someone standing downhill of the box trying to stop it from hitting the spring. Until the person gets crushed between the box and spring.
Be a heavy box. It is 5 code.
Oh, no.
Or a weak person.
The person gets bruised. All right. Because this doesn't, no work, so the work non-conservative is 0 joules. Energy is conserved, and so my initial energy is equal to my final energy. What are my two types of energy?
Potential and kinetic.
K initial plus U initial is equal to K final plus U final. What are the two potential energies associated with this problem?
Gravity and elastic force.
So we have K initial plus U sub G initial plus U sub S initial is equal to K final plus U sub G final plus U sub S final. And now the formulas.
So, kinetic will always, like that's the force of whatever our spring is, right? Or is that our elastic force?
What?
K
K is the energy associated with speed.
Okay.
1/2 mv squared.
Okay.
Sounded like a chorus of one voice. That was so incredible.
That's the only one I can tell you though. That's where.
Hey, that's the important one right there. All right, gravitational potential energy.
MGH initial?
Elastic potential.
Well, you were just talking about the derivation,
Yeah.
so.
Yes, I was.
1/2 K something.
Kx squared.
Initial. This K right here is the spring constant. It is a lowercase k. It is not kinetic energy. And then all of that except final. So 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. And again, delta x versus x. Some books will just put in x, but it's the displacement from, or how far has the spring been changed from its natural state.
And the constants cancel out in this case, right? So we don't use them?
Correct.
Okay.
All right, so can we get rid of anything, or do we need to define anything?
Is the box moving when the problem starts, or is it still in the problem?
Ah, well, let's start it at rest. Initial speed is 0 meters per second.
So we can cancel out the first term.
All right, so speed I equals 0.
And we can cancel out the 1/2 K delta x initial.
Why?
The delta x is 0 at first.
We can get rid of two more things.
Is the final velocity also equal to 0 because the box will have a velocity velocity of 0 when the spring is fully compressed?
Yes.
And maybe the last term, the K delta X final, because it'll put it back where it started from the spring.
If we're looking at the place where the object stops, then delta x is not 0.
Okay.
So these have to be at the same moment in time.
Okay.
And then,
Should we call the final height 0?
Yes, Amy?
Would it be MGH initials, wouldn't that be 0?
Could be one of, either of you could be right. It's just a matter of where do you want it.
yeah, where's our origin?
I heard Anna first putting h is equal to 0 at the bottom. Amy wants 0 at the top.
I think if we do 0 at the top, it'll be really easy because the left side of our equation will just be 0.
Well, we have to do slightly less algebra.
Yeah, let's do that.
But then again, wouldn't we have to make MGH final negative?
It will be a negative
Yeah,
number.
it would be negative.
So it,
Decisions.
mathematically, I don't know if there's, you save a half a second one way or the other. Either of you have strong feelings? I traditionally put, well, the trouble is, let's go back to what Anna said. There actually, we might run into some issues. Where is the final height?
Final height is when the spring is fully compressed.
So somewhere down here?
Yeah.
So we don't know exactly.
Right.
Well, we can sort of, right? Because if we've got the length of 3 meters and then we've got the x that we're presupposing,
Right.
we
Wait,
can
so
use
if we
that.
define the final, can we choose to define the final height at 0? Like regardless of where the spring is going to be compressed to?
Yeah, we can.
Okay, because that might be easier, instead of worrying about having to find the height and knowing it's going to be a negative number.
Choosing the right value, or choosing where to make h is equal to 0, top here, or I tend to pick it right at the point. You know, when the mass has gone a distance of L, that's when the h is equal to 0. It all depends on where you want to put your math. This is fine, that's fine, that tends to be what I put it, where I put it, but
If you put it, wait, L, so it would be not to the full compression of the spring, it would just be that distance between the spring and the mass, where
Like
you
very
would
top,
put 0?
like just barely touching the spring.
yeah, just barely touching the spring. Now, I'm noticing that my drawing here is just a little bit off. I'm having difficulty with dimensions here. So if the final compression is there, I guess technically that would be where h is equal to 0. Because the initial height would be to the front edge, and that's where the front edge would be. All right, so let's just see what happens with h is equal to 0 there. We'd have, if we'd gone with Amy's suggestion of h is equal to 0 at the top, the only difference is what we will now have as my initial height would have been my final height with a negative sign thrown in there, if we'd gone with Amy's suggestion.
Which is just 3 plus x, or negative 3 plus x, depending on which way we went.
Well, there's one other factor that needs to be taken into
Oh,
account, but
yeah, right.
because height is a vertical thing.
Got it.
All right, so we have now reduced it to that.
Wait, so what did we end up canceling out?
The final.
So, oh, that's right.
Because Amy said so.
Or Anna. So we have mg initial height equals 1/2 k delta x final squared. Simplifies down to something quite nice. All my gravitational potential energy becomes elastic potential energy. Now, initial height. We're basically dealing with a triangle here, with a hypotenuse of L plus X. This angle right here is our theta. So this height is L plus X sine of theta. That is what the initial height is. Biggest mistake I see students make is they forget about the fact that it's vertical and they go for an initial height of L plus X. So we have M G L plus X sine of theta is equal to 1/2 K X squared. The spring only compresses the distance X, and I probably should have used a different letter since I'm using delta X for displacement. X is just this distance right here. And we are solving for X. So I have mg L sine theta plus mg X sine theta is equal to 1/2 kx squared. I have a quadratic since I'm solving for X, and that is a squared term right there. We are dealing with a quadratic equation. And so I need to get it into a form where I can use the quadratic formula. So I'm going to get everything over on the right side. And that is just personally because I just like the quadratic term to be positive. That's just my own thing. So 1/2 kx squared minus mg sine theta. X minus mgl sine theta now at this point I feel it's easier to plug numbers in as opposed to waiting until the very end, because I have a feeling with all that we'd end up with a mess under the radical. So this is 0 is equal to 10x squared. Yeah, okay, it's 20. So mass is 5, g is 10, and sine of theta is 0.6.
It should be just
30.
6. Oh.
The-
Oh, my bad. Yeah.
Minus, so L was 3. So this is 5 times 10 times 3. So it's 150 times
0.8. Or no, not 0.8.
times 0.6.
It was 90.
It does not always work out as nicely as this, where I have
Quadratic.
the convenience of, I can just divide by 10 to simplify it. But it does in this case, so let's do it. Minus 3x minus 9. Unfortunately, it does not factor simply from this. We do end up with some decimals involved. So x equals 3 plus or minus the square root of 9 minus 4 times 1 times negative 9 over 2. That's 36. X is 3 plus or minus the square root of 45 divided by 2. We will end up with 2 answers. One of which makes, they both have physical meaning, one of which actually answers the question.
I'm guessing it's the positive answer.
Yeah, but I want both answers anyway.
Okay.
So
I'm 4.854. Forgot what x is, meters.
-1. I'm sorry. Yeah, 1.854 meters.
you got the same? We get confirmation? Yeah, all right. So, All right, we have our two answers here. Let's just double check just to make sure energy is conserved. So we have initial and final. A pause here for questions before we actually do a quick check.
I got just a little bit lost when we changed from delta x to x.
So the formula has delta x in it. This is the displacement from equilibrium. I just said x was how far the thing actually compresses from its natural state.
Right.
If it helps, delta x is the basically x final minus x initial. And I'm just going to make, if I make x initial 0, I just say that this is where x equals 0.
I guess I thought the displacement would be from where the box was started at the top.
No, because this is the energy that is stored in the spring itself, and so it has to deal with what happens to the spring. Before the box actually touches it, it's not storing any energy.
Okay.
Is that sufficient?
Yes, thank you.
Okay. Other questions right now? Brooke?
Yeah, how did you go from the change in x at the very top where it's like, yeah, how did you go from that to the just x squared? Because is it because the change in x is there isn't a change in x?
No, it's.
That's what we're trying to find.
That's what we're trying to find. If I had made this instead of x, I had picked y to be the letter, then this would be y.
Okay.
This is just how much the spring, because the spring starts out in some natural length.
Right.
When the mass hits it, it starts to compress. So that what I called x was just how far it compresses.
Oh.
That's what this number here is how far a spring is off of its natural state.
Okay, that makes sense. Since the change in x, that's what we're trying to find anyway, so you just have it as x down
Yeah.
there. Okay.
Okay, so the only reason we could do that is because our height at the bottom, the final height was 0.
Correct.
Okay,
If our final height there was not 0, then
we just have to keep it at delta x.
no. That part would not change.
Okay.
It's what would change is this bit right here. If you made the initial height,
0.
there's a lot of different ways of approaching it. That's
Yeah,
right. If the initial height were 0,
that would be gone.
then that would be gone. But over on the right hand side, you would have basically negative mg L plus x sine theta.
Okay.
If we had chosen what I typically pick right here, then the initial height would have been mg L sine theta, and the final height would have been negative mgx sine theta,
Okay.
and it would just split it in two.
Okay. I
You
like
can
how
write
we-
that down.
Huh?
You're saying okay. I mean, do you want to
Yeah.
actually write that down, or?
Well, I've got it. Like, I'm just trying to think about it. We ended up with the same result either way.
Oh, yeah, absolutely.
Because it was just a matter of moving it from one side of the equation to the other.
Which is part of the freedom we have. Brooke?
From mg L plus x sine theta to the mg L sine theta plus mg x sine theta, it's just broken up because you distributed, right?
Correct.
Okay, gotcha.
We'll put this back to x, which is what we originally had. Lisa?
Will the height, so if we assume that at the bottom is 0 and that at the top is some number,
Uh-huh.
would the height always be L plus x?
So if we assume that the bottom was 0, which we did,
Yeah, and the initial is something, then would the initial height always be L plus x?
times the sine of that
Oh,
angle
yeah,
there.
Yeah, that's it.
Given the way I set it up, yes, if h is equal to 0 there, the initial height has to be that.
Oh,
I'm not, all right, so let's take a look at it slightly differently. So if that is L and that is X. And so we did h is equal to 0 down here. So if I picked h is equal to 0 here, as Amy had suggested, then my final height H final would be negative L plus X sine theta.
Okay. I got confused with X. I forgot that we have to add it to like, get our, like, the whole thing. So it makes sense now.
Good. And just one other thing, sort of tagging on to something I had said earlier. So that was L and X. If I had chosen, oops, not that. If I had chosen H is equal to 0 at the point where the mass first comes in contact with the spring, before the spring has a chance to compress, my initial height would be L sine theta. My final height would be negative X sine theta. There's not necessarily any advantage to one system over the other. In this one right here, you're not distributing, but you have something on both sides of the equation. You end up in the same place then. Right, other questions before we do a quick check to see if we made a mistake?
Are you gonna erase anything? Okay.
I was going to erase the stuff I just drew.
Okay. Yeah, no, that's fine.
All right, so we have kinetic, gravitational potential, and elastic potential, or spring potential. And then K final, UG final, US final. That was 0 joules. It starts at rest. This is 0 joules. It ends at rest. This would be our mass 5 times 10 times our initial height, which is 7.854 times 0.6. So what is that?
Hold up, yep, 235.62.
And this was 0. So my total energy to start with is 235.62 joules, assuming that anyone, same thing, all right. Down here, my final spring potential is 1/2 times K, which is 20, times how much the spring was compressed, 4.854 squared.
Yep, same with her.
Because energy is conserved. There's basically, that was the condition that we set up our equation for. It better come out right. We basically have identified that we did not make a careless math error. Doesn't guarantee our initial equation was right, but I'm feeling good. I'm about to add, before I add friction, I was going to add 2 other questions. All right. So the spring comes down and it compresses it almost 5 meters, and then it bounces back. How far up the ramp will the mass go?
7.851 meters.
Yeah, it should end up exactly where it started. Now instead, is there a problem, Anna?
It's minor, but I have 235.61 and not 0.62.
Oh,
I think
okay.
that's because we didn't use the whole number for the meters, so when we square it, there's just a tiny bit of an number, so.
Got it.
All right. The spring comes down, the mass comes down, hits the spring, and attaches. Maybe there's super glue acting on it, but sure, we'll pretend super glue works that quickly. The mass hits the spring and is now attached to the spring. Now how far up the ramp will it go? Because before, it's going to, when the spring gets back to its natural equilibrium position, the spring would start to slow down naturally once it passes equilibrium, but the mass would be slowing down actually at a different rate. But the mass should end up back where it started, but when it's attached, it will not.
Are we assuming that there's still no friction here?
Yes, still assuming no friction.
Does that add tension force?
And well, it's still, because it's attached to a spring, we're going to throw it into elastic. So I need to, I want to keep those two numbers there. So we had 4.854 meters and negative 1.854 meters.
So now we're adding in the fact that it attaches to the spring.
Yes.
Okay.
And it's going to bounce back up the ramp, but it won't go to the initial position because the spring is going to, every time it tries to get out, the spring pulls it back in. Still, energy is conserved. The only two forces that are doing any work whatsoever are the spring and the force due to gravity. They are both conservative forces. We got H is equal to 0 at the bottom. E initial equals E final. If we keep H in the exact same spot, then, well, this seems like this should be about 235.62 joules, 1 joule, whichever one was closer.
It was 6.2?
I think the 6.2 is probably more accurate.
Okay. I know what my initial energy is.
And it's equal to energy filed, so we know it's the final. It's equal to the final energy, so it's also 235.62.
Except we have an unknown here. So we have K final plus UG final plus US final.
Yeah.
That meant 3 types of energy involved in this problem. If you want to write down every single possible energy equation, you can, and just you'll get rid of most of them. So this is, all right, let's do this as a group. What's the formula for kinetic energy?
1/2 mv squared.
So nice.
Are we gonna get rid of that one though?
We will.
Okay.
We learn it just to get rid of it.
Final plus, 1/2 K delta X squared. Yeah, final.
All right, so as Brooke said, 0. Because it's going to extend until it stops moving. The 0.
We can't get rid of MGH because H isn't gonna be 0, right?
Correct. So our unknown is how far does it go back up the ramp. I can express this in terms of where it's at maximum compression, or I can express this in terms of this point right here. Just like when I defined how far did this get compressed, I defined it from the natural state. So I can do the same thing here. Personally, I think it's a little bit easier if we define it from the natural state. Because otherwise, if I define it from down here, so let's say I call that Z. My delta X here would be Z minus 4.854. Because the spring is getting less and less compressed until it gets to here, and that delta X is how far it's from equilibrium, not from its initial position. So I'm going to define Z as how far it extends beyond its natural position.
So Z will be, where it starts will be from back where it's natural, and then the added weight of the mass pushing it back out.
Wording was off. Try again.
Okay.
I got thrown off by some of the wording.
Z is from where the spring goes back to its natural state,
Right.
after compressing, and then extends because of the weight on the mass, or the what causes? Is it just the conservative work that causes the spring to contract or to expand?
It is doing, well, yes, initially it is conservative work causing it to expand, and then it'll be conservative work causing it to slow down as it extends.
Okay. Okay.
So this will be, there's a plug in numbers, that's 50. Times my final height, which will be x, not doing x there. It'll be 4.854 plus z times the sine of the angle, 0.6, plus 1/2 k z squared. If we had chosen to define z based upon its starting from its maximum compression, we'd be squaring a binomial.
Where does the 50 come from?
mg. Yeah, I just went ahead and did the multiplication now.
Okay.
We still have a quadratic. So 235.62 equals so that's 30 there, so 30 z squared.
Oh, okay. I was confused. You're good.
50 times 4.354 is what you're looking for?
Where-
242.7
Times 0.6.
is 145.62.
Questions to hear?
Are we gonna subtract 235.6? Yeah, okay.
Yep. So 0 is equal to 10z squared plus 30z minus 90. Very similar to the equation we had before. The big difference is that we've got a plus here instead of a minus here.
Is that minus 100? That was a great new math in my head. Is that not right?
No, for
145.62 minus 235. So it's negative 90.
It is. Yeah, I did something wrong.
So 0 is equal to z squared plus 3z minus 9. Therefore, z is equal to negative 3 plus or minus the square root of 45 divided by 2.
What?
That's the
Same
same
thing.
thing as before.
Well,
Right.
no, it's
Before we had a
negative.
positive 3 here.
Yeah.
Okay.
So what does that do to our answers?
Flips them.
So now it's the 1.8, 1.8 millimeters?
That's what the meaning of the other number is, because ultimately, mathematically, what we have here is we have a certain amount of energy to start with. We have 235.62 joules of energy. We were looking for another point where we have the exact same amount of energy, but the kinetic is 0. Well, it occurs at that maximum compression, and it occurs at this point, assuming that the spring has been extended. Because the initial equation, we assumed that the spring had actually stretched some, and so that's what that's the physical meaning of the other answer.
Okay.
Real quick, to put it in like terms of like what's happening, like the spring, this would be if the spring attached to the object and traveled up with the object after it compressed?
Yes.
Okay.
Den, Brooke? Brooke, then Den? One of you?
Oh, okay. We figured out the value of x before we even talked about attaching the mass to the spring and then finding z.
Right.
So we didn't have to do this, did we? Is it always gonna, the like other value that square root gives us, is that always gonna give us?
Assuming no loss in energy, yes.
Okay.
So when we introduce friction, we don't get to do that.
Okay, fine.
Den? Oh, same, okay. Any other questions before we throw friction into it?
So we wouldn't account for, no, we already did in the equation. I was gonna say we wouldn't account for the distance that it would take for the spring to compress, but we already did with MGH final.
Yeah, that's right there. That's when we took into the account how much the spring compressed.
You said the reason why we get these two answers, the like 4.854 and the 1.854, we get those because you said it's like, where is it gonna have the same energy?
Yes.
Okay. That like kind of makes sense. It's like wowing me right now that this math problem knows where it's gonna stop if the mass is like attached to it. Like,
The beauty of physics.
yeah.
Assuming-
Or the beauty of math, depends on which side you want to come from.
Assuming there's no friction, of course.
Right, we're assuming no loss of energy.
Ideal spring,
Yeah, that's a beautiful thing.
basically perfect conditions.
Yes. But isn't that what life is like?
Like, yeah, that's exactly.
Sure.
If you listen to Mello.
If you look what?
If you listen to Mello.
Oh. All right, side friction.
Oh, okay.
Well, it shouldn't be that hard, right?
I mean, it's just one more factor to throw into it.
That was your turn to say, yeah, of course.
Yeah, of course.
It's not that easy. It's not that, I mean, it's not that hard.
So this time I'll actually use a different letter. Do we still want to stick with H is equal to 0 here?
Yeah.
Is that a trick question? You trying to
No.
help us out?
It's a question of, do I need to erase this and write it elsewhere?
Okay.
Let's see, what letter do we, I'm going to make this one Z. We now have friction involved. Look at it. So we have friction acting back, we have normal force acting this way, we have weight acting down, and then eventually there's going to be this spring force acting up the ramp. Ooh, oh man. Weight acting down. And weight breaks up. We've done this before. We do need to go through at least this part of it. This would be W sine theta, W cosine theta, normal force, friction. And I'm going to go ahead and throw spring force into it at this point, even though for the first 3 meters of movement, it's not involved. We still need to break weight up because I do need to figure out what the normal force is in order to figure out the friction. So my friction is going to be equal to mu, but it means step mu y, which in this case is mu mg cosine theta. Sort of rushed through that because I feel like we've done that several times already. But if you need me to drop back, please ask. Okay.
So it's,
Before, our non-conservative work was 0.
Yeah.
It's not now. So this is basically friction times displacement is equal to E final plus minus E initial.
Okay, hang on, 1 second. Wouldn't the sine and cosine be swapped? Because down the ramp it's going to be cosine, and into it it's going to be sine?
No.
Oh, the angle would be at adjacent, right? So, I'm sorry, you've got it like this. Well, for your perspective, it's like this.
So we've got, so weight is acting down. This angle down here is theta. Whatever you're breaking up is the hypotenuse of its own triangle. That's a 90-degree angle there. So if that's theta, this is theta prime. That's a right angle here, so this would be theta down here.
Okay,
So the opposite is sine.
okay. All right, thank you.
All right. So therefore, I take my initial energy plus the conservative work. Now I know that the friction is opposite direction of displacement, so minus F delta X is equal to E final. And so now we go through the same process that we have done. K initial plus UG initial plus US initial minus F delta X is equal to K final plus U final plus UG final plus US final. The formulas, just like before, 1/2 mv initial squared plus mgh initial plus 1/2 k delta x initial squared minus f delta x. Ooh, there's some really sucky notation here. Because those two delta x's I just have written down are not the same delta x. This is the displacement while friction is being applied, and this is the change from what the spring, basically the spring compression.
Why
So,
don't say delta Z?
delta what?
Delta Z, since it's the distance? Or is that
Or
already?
just, all right. Yeah. All right, that's L plus Z right there, and that's 0. Ultimately, initially, that's what's going on.
Okay.
So it's the initial 0 squared. All right, so that's equal to 1/2 mv final squared plus mgh final plus 1/2 kz squared.
Are we still able to get rid of 1/2 MVI, I'm sorry, 1/2 the MV initial squared?
Yep, still starting at rest. And what else can we get rid of?
1/2 K here, I would say.
Because 0 equals 0.
Should we get rid of friction, assuming, well, no, friction's there even if the objects are at rest. So
Yeah,
that's-
we can't get rid of friction.
Yeah, that's what I was saying.
If we got rid of friction, then
Would
the answer is 4 point.
friction Yeah. 1/2 MV squared final.
Still looking for maximum compression.
And then the MGH file, because we still have the resistance here.
I believe that was.
That's
And there we go. It has an initial height because we said equal to 0 at the bottom. There's friction involved the entire way down, and the spring's going to compress. So we've got the 3 terms involved. MGH initial equal minus FL plus Z is equal to 1/2 KZ squared. So this will be MG. So my hypotenuse is L plus Z sine theta minus UMG cosine theta L plus Z is equal to 1/2 K Z squared. Let's stick numbers in. Distribute first, then stick numbers in. So we have mg sine theta times L plus mg sine theta times Z minus umg L cosine theta minus mu m g z cosine theta is equal to 1/2 a z squared. Now let's stick in numbers.
We're solving for z, which means we have to have a mu value, is that right?
Oh, yeah. That was 90. Let's see. So MGL, that's 150 times 0.8. Okay, so this whole thing is 24. You're not getting the same thing?
I am.
Oh, good, okay. The look in your eye was, something was off. And so this, since I don't know z, is something z, 8z is equal to 10z squared. So before, these two terms were not here. Introducing these terms is basically, you got two negatives in front of it. We are taking energy out of the system. It's a quadratic because I got a squared term here, so I have 10z squared. Then I have,
No, it's negative 10c squared. Or,
sorry,
yeah.
0 equals, bringing everything over to the right side.
Okay.
I have 22z, which I'd bring over, so
Minus 22b. Wait, yeah, no.
It's minus 66.
Yeah.
I could divide by 2 to simplify it a little bit, but to me, it doesn't really seem worth that effort. So I end up with z is equal to 22 plus or minus the square root of 22 squared minus 4 times 10 times negative 66 divided by 20.
Uh, 29.36. And then,
Did you divide by 20?
well, I did, it's all over 2a, right?
Yeah, a is 10.
Yeah, I did the divide by 2 route, which should be the same answer. I divided by 10 rather than 20.
Why would that give you the same answer?
Because I did 11.
Oh, you
Five.
divided by 2 at that point.
Yeah,
Okay, so what did you get for your final answer?
29.359.
That doesn't seem right. What'd you get, Anna?
I did the negative value. I did 22 minus, I don't know if it's right, but I've got
Oh.
negative 1.69.
I got that.
Negative 1.69?
Yes.
Yeah, that's what I got for the negative, and for the positive, I got 3.89.
That is also what
And you also got, okay. Let's go another decimal point.
3.895.
And I assume 695?
Yes.
All right. Now, the one reason why when I heard 29 was that I knew that couldn't be right because without friction, it went down 4.8 something. With friction, it's not going to go as far. So that would make more sense.
Also, this is just really short for 29. Like,
Yeah. Let's check our answer. Questions before we check our answer?
I think I figured out what I did wrong.
Okay, good. Right, so there's my initial energy right there. So that is 0 joules. My initial gravitational potential would be 5 times 10 times,
What was it, the cosine of plus c cosine 37?
6.895 times 0.6. Sorry. It sounded like you said something different.
Don't worry about it.
I was saying like the cosine, yeah, don't worry about it.
Okay, so what does this end up being? Because the length is 3 plus whatever it compressed.
206.85.
206.85.
Yes.
And this is 0 also. So I start out with 206.85 joules of energy. And I now have to distribute it. First thing I do is start giving it over to kinetic. It hits the spring, kinetic starts giving it back to a different potential. Kinetic is having an affair with a different potential, start giving money away. I started with a money analogy, then I thought, how does that you extend that? So, the amount of inner work that was done by non-conservative force, we have our friction right here. So that's 0.2 times 5 times 10 times 0.8.
8?
Okay, so that was 8 times how far the friction goes. So this would be negative 8 times 6.895. The friction force times how far it was dragging.
Got negative 55.16, but I'm not using the full value, so I think it's.
All right, so somewhere around there,
Yeah, it's the same.
0.16 joules. And then final. This is 0, this is 0, and this is 1/2 times 20 times 3.895 squared.
Something like 151.71 joules.
Let's see if that makes any sense. We started out with 206.85. We lost about 55 of it, and we end up with about 150 of it.
Yeah, that's what I got too. 150.
All right. So whether our initial equation was right or not, we at least seem to have solved the equation correctly.
So for our question, which is how far will it go back from being, how far will the mass move after being compressed and then the friction acted on it? For our final answer, would that be 3.895, or are you looking for how much work is done?
Initially, the question is how far did the spring compress? So it's the 3.85
Okay.
meters. 3.895 meters.
But the absolute value of the negative z value would be how far the spring would extend where the mass attached?
No. It's not going to work that way because
Yeah.
it's going to lose more energy as it goes up, so we don't. And even if I came in and said, all right, so now magically the friction disappeared. As soon as it hits compression, it flips a switch, friction's gone. You still have to go through the math again because one solution put it out, the negative solution put it here, but there's still energy lost between the negative solution and what was the actual answer. So other variations of this problem are it starts out on a frictionless ramp and then suddenly friction hits when it gets to the spring. Or it has friction until it gets to the spring. You know, there's basically variations like that.
Variations that we will see in this class?
Depends on my mood.
Okay.
Could I actually write down the, oh, -3. There we go.
So it'd be a negative value since it's,
Now, the spring compressed 3.895 meters.
gotcha.
If you say it compressed negative 3.895 meters, that implies that the compression was negative, so it stretched.
Okay, gotcha.
I guess you could, if you really wanted to, say it stretched negative 3.895 meters, but I don't think it's worth it.
Yeah,
But then again, I had a student, because radians are a unitless unit, and you can always stick radians onto anything. I had a student who kept writing radians after every answer, in addition to what the correct ones were. I would not think it was worth it, but he was abused in Nelson.
good for him.
Yeah. Yes, Ben.
Why is the W cosine instead of W sin?
Why is this one
Yeah.
cosine? I need to erase. Because we're breaking weight up. Since the acceleration, well, ultimately I need to know the normal force, so I need to figure out what's opposing that. What is the normal force opposing? So I need to break weight up into its components, the perpendicular components. So if I'm breaking weight up, it is whatever force I'm breaking up is the hypotenuse of its own triangle, and I'm trying to find the smaller parts. And so if my angle theta is, this is theta down here, I have actually 3 right triangles here. I've got this right triangle here, this right triangle here, and then the big one, the big right triangle. Weight is acting straight down, so it is perpendicular to the ground. Theta is defined based upon the ground. So since that's a 90-degree angle there, this has to be 90 degrees minus theta for that right triangle. Looking at this, I have a right angle here, and so if this is 90 degrees minus theta, this angle down here has to be theta. Therefore, looking at what I'm now highlighting in blue, my opposite side, the one dealing with sine, so if this is weight, this would be weight sine of theta, and the adjacent would be W cosine of theta. So the normal force is opposing W cosine of theta. That's where that comes from. Other questions right now? So, I guess, got the test next Wednesday. Monday, we'll start out with any questions, so you can ask questions about the test if you need to. And then we'll start talking about momentum.
Was this chapter 7?
Chapter 6.
I think it is. Yeah, because 4 and 5 were Newton's laws, 6 was rotation, centripetal motion, satellite motion.
Yeah, I mean, this is momentum part of chapter 7, or is it?
No, it's the next chapter.
Yeah, okay.
I'm guessing since we did the lab that we did on Wednesday, is that going to be due the Wednesday after the test?
Yes.
Okay.
If you have it this Wednesday, this coming Wednesday, great, but not necessarily where you need to put your priorities.
Okay.
But you know you better than I do, I hope. At one point, I thought I had this great insight into myself, and I shared this with somebody, and the person looked at me and said, "No kidding."
You're wrong.
I was just, that person knew that about me before I did.
Yeah, to the best of it.